Okay, so as in the last video we have discussed about the maximum velocity of the projection of a particle which is moving along the uniform circular path and the minimum velocity of that projection, right? What we found the maximum velocity of that particle was vq is equal to omega x naught, and the minimum velocity was of course 0. Alright, the maximum velocity we found at mean position and the minimum velocity we found at extreme position. Today we are going to derive the formula for finding the acceleration of the projection of a particle which is of course moving along the uniform circular path, right? So what we are going to do today is we are going to derive the formula for the acceleration. Driving the formula for finding acceleration. Of what? Of course particle or projection. You must write projection here, right? See, what we are going to do today is we are going to find the formula, or we are going to derive the formula for finding the acceleration of a projection of a particle, right? Now see, to understand we must make a figure here, right? So this is figure. Now this is the radius, since we are making its projection on the diameter of the circle. This is not radius, this is diameter, right? This is its center point, right? For example, here particle is moving, this is particle, right? Here it has its projection, this is its projection, which is denoted by q, right? Now we know that it will gonna have an acceleration towards the mean position. We have already discussed in the simple harmonic characteristics that the projection will gonna have the acceleration towards the mean position, which means it will gonna have acceleration towards the mean position. See, now acceleration is a vector quantity, which means now we must break this vector into its components. We must resolve this vector in its components, right? So one would be this component and other would be this component. Now see, this is making angle theta with this component, which means this is particles x component, and this is particles a p y component. Now see which component of a particle is responsible for the acceleration. You must see apx is responsible for the acceleration of a particle. Apx is responsible for the acceleration of particle. So let's write this here. Acceleration of shadow is equal to the x component of particles velocity, of particles acceleration, particles acceleration, which means now I can write like this, that the acceleration of q shadow is, you know what, equal to apx component. since APX component is responsible for the particle's acceleration. That's why we have written what? We have written AQ is equal to APX. Now see, AQ is equal to, instead of APX, I can write AP cos theta, right? And we know that in uniform circular motion, the centripetal acceleration is omega r square, So let's substitute this value here. AQ is equal to, instead of A, now I can write what? This was is equal to minus AP cos theta, right? So minus r omega square, instead of AP I have written r omega square, and cos theta same. Now you can remember one thing. We have already derived the formula for the displacement of the shadows particle, right? So that was equal to r cos theta. Now you can see, you can find here r cos theta too. Wait, let me rearrange this. For example, minus omega square, I can write r cos theta. Now see, r cos theta, we have already learned x is equal to r cos theta, which means instead of r cos theta, I can now put what? I can put x. So let's put x. AQ is equal to minus, instead of r cos theta, x, and omega square same, right? So this is the formula for finding the acceleration of a shadows of particle. Minus x omega square. What? Minus x omega square. Now see, since this motion is uniform circular motion, let's prove that is this a motion is simple harmonic motion or not. And to find that the given motion is simple harmonic motion or not, we can actually find that its acceleration would be directly proportional to the negative of its displacement, which means we must prove this now, right? So since the motion is uniform circular motion, so omega, we must make omega equals to constant, right? We must make omega equals to constant. So if I rearrange this formula, I can now write AQ is equal to minus omega square x, right? I've just rearranged this. So now I have to make this omega as constant is equal to minus, instead of omega square I can write constant x. Now see, after removing proportionality sign, we get is equal to sign and constant. So for removing is equal to sign and constant, I can now write proportional, right? Since now I am removing is equal to sign and constant, so now I have removed is equal to sign and constant, I have got proportional minus x. See, this is proved that the given acceleration is simple harmonic motion, since acceleration is directly proportional to the negative of its displacement. So now we have derived the formula for finding the acceleration of a projection of a particle which is moving along the circular path, uniform circular path, and the formula we have got is minus x omega square, and at the end finally we have proved this too, that this particular motion is simple harmonic motion by proving that acceleration of a particle is directly proportional to the negative of its displacement, which of course means it is simple harmonic motion.